Welcome everybody to this presentation on green chemistry, some methodologies and applications. In the first lecture, we looked at what is green chemistry and why it is important. So we know that green chemistry is important because the chemical industry is multiplying. The need for materials due to increasing population and demand for new technologies based materials is increasing. And therefore, we have to look at how this multiplying chemical industry could be made to employ new methodologies, new technologies, new processes, so as to make them less polluting, make them green technologies. So we saw that green chemistry is nothing about waste minimization at the source, rather than trying to remove the waste or separate the waste or process the waste. Use of catalytic reagents in place of reagents which are required in stoichiometric amounts. And not only this, we also saw that the catalyst should be recyclable, preferably. We should use non-toxic reagents and renewable resources should be employed. Improved atom efficiency. Improved atom efficiency obviously means less and less waste produced. And then use of solvent-free reactions. Can the reactions be done without solvent under solvent-free conditions? Or we can use recyclable, environmentally benign solvents. So it boils down to nothing but again saying that it is our green chemistry is minimization of waste, hazard, risk, energy, and cost. How to achieve all this? That was the third question, and this is what we are going to talk about the processes here. So some of the methodologies which are employed or which can be employed to achieve the desired goals. Some of these are listed here, and I'll speak about each one of these in very brief. The details are readily available, and one can look into details whichever area one feels interested in. And I believe there's a lot of scope in each of these methodologies. First of all, we'll focus on sonochemistry and microwave. In fact, these two techniques are used to make the reactions faster. Let's first take up sonochemistry, which is nothing but application of ultrasound in chemistry. That is doing reaction under exposure to ultrasound. It has been found that the reactions which required hours and days can be completed in few minutes. Reactions which are going very slow and were not complete proceeded to a much higher extent under ultrasonic exposure. Ultrasonic exposure works by employing quartz crystals, and the reactions take place under high energies and high pressure on a very, very short time scale. Most of the reactions are believed to be taking place in and around cavitation bubbles or the collapsing cavitation bubbles. The different types of reactions which can be done include the homogeneous reactions, heterogeneous liquid-liquid reactions, and heterogeneous solid-liquid reactions. Some of the examples like Grignard reaction, Reformatsky, Ullmann, Barbier, Woods, Dickman, and so on. Here we can see that many of these reactions are employing metals. So even heterogeneous reactions which employ metals as a reagent can be easily done. It's also said that exposure to ultrasound breaks down the metal to much smaller particles, thus increasing their surface area and making the reactions much faster. There's no limit on the kinds of reactions which can be done. The other very well-known technique, I think almost every chemist working in university must have employed, is the microwave-induced reactions. Initially, yes, it was used commonly because reactions could be done in regular microwave, which is used at home. But now I think the journals will not accept that, and one has to do these reactions in special microwave reactors under controlled conditions. Here again, the reactions which are slow, which takes days or hours, could be done in minutes. Our reactions could also be done in few seconds. Reactions could be done in solution phase, but the solvent played an important role. More polar the solvent, more microwaves it absorbs and makes the reaction faster. Reactions under solvent-less conditions have also been done in microwave. And here, reactions which are supported on reactions between supported reagents and substrate. That is, we could support the reagent or substrate on a support, an inert support like silica, zeolites, alumina, etc., and then do the reaction without employing any solvent. No doubt, later the product separation will involve some solvent. Similarly, phase transfer catalysis in absence of organic solvents. And then the reaction between neat reactants or neat reaction, that is not even a solid support is required. We simply mix the reactants and expose to microwave. Many reactions have been done under these conditions, and it was found that the reactions are very rapid, can be completed in a very short time. The clean reactions, there's less purification required and hence less waste is generated. Green solvents, as we shall discuss about what are green solvents, can be employed. For example, I would say water. Very minimal solvent usage is required, if so. And then, of course, the energy input is very low. Microwave has a very low energy. So these are the advantages, and thousands of reactions have been reported and papers in this reference. Next, we come to catalysis, a very important component of organic synthesis. In fact, catalysis is one of the fundamental principles or fundamental pillars of green chemistry. Catalytic processes are far more superior to stoichiometric processes and make the reactions highly efficient, economical, and are responsible for high yields of products in a shorter time and also reduce the byproducts in the reactions. So one should try to use a catalyst for doing a reaction and not do reaction in the stoichiometric process. Green catalysts are the catalysts which are eco-friendly because catalysts again could be toxic. These can be regenerated and hence reused multiple times and thus minimize waste production during process. And this is what we said. we should preferably use recyclable catalyst. So the green catalyst should be non-hazardous and non-toxic, should be easily separable and preferably recyclable, should be economical and easy to prepare or obtain. Phase transfer catalysis, one example, has been known for I think almost 5 decades. Various types of reactions which can be done under phase transfer catalysis are shown here: liquid-liquid, solid-liquid, solid-gas. And the advantages of phase transfer catalysis are reactions are very fast. They don't require expensive aprotic solvents, don't require high temperature because can be done under room temperature and also under anhydrous conditions. The workup is easier because products can be separated simply, and high yields are obtained by suppression of side reactions. See, look at the example of a simple substitution reaction like 1-chlorohexane. If you do with sodium cyanide, under normal condition, the reaction yield is not even 10% after 2 days. But if you do the same reaction in a phase transfer catalysis, the reaction can be completed in just a couple of hours, and hence the advantage. And so many applications of this are known. All types of reactions have been done under phase transfer catalysis. Light can also be used as a catalyst for chemical reactions. Biotransformations and biocatalysis. Yes, enzymes display 3 major types of selectivities: chemoselectivity, regioselectivity, and diastereoselectivity, and enantioselectivity. We all know that enzymes are classified in 6 different types, and they offer various advantages. For example, these are very efficient catalysts and very, very specific. They are environmentally acceptable. They act under very mild conditions, mostly room temperature. Their enzymes are compatible. The enzymes are not bound to their natural role, and enzymes can catalyze a broad spectrum of reactions. There are no doubt some disadvantages also. In recent years, last say 2 decades, there has been a lot of focus on applications of nanoparticles, and these have also found application in organic synthesis or other synthetic processes. And here, I think one advantage is if we have a catalytic process, yes, one could make these nanoparticles of those catalysts and use, and this could be easily separated, recycled, and the process have been quite streamlined. And again, nanoparticles also offer a variety of advantages. It's a high surface to volume ratio, high catalytic activity, reusability, high stability, required in low amounts, highly efficient and selective, greener, and easy separation. And a variety of reactions have been done under this condition. Then we come to a solvent. We said that 80 to 90% of the waste comes from solvent and the separation techniques. So we should preferably use green solvents or recyclable solvents. What are green solvents? Ones which have low toxicity and are non-hazardous, which are easily recyclable so that there's no disposal, easily removable from the product. They must have low reactivity and must be cheap. These are some of the preferred solvents. If you could do reactions in water, nothing better than that. Is probably the cheapest solvent and could be easily purified. Ionic solvents. There has been a lot of interest in ionic solvents as green media. Now, of course, it's big question mark whether it's really green or not. But what are ionic liquids? Ionic liquids are defined as compounds consisting of cations and anions which melt at or below 100 degrees centigrade. Many are liquids at 25 degrees centigrade, and these are sometimes called as room temperature ionic liquids. Advantages of ionic liquids include that they have negligible vapor pressure. That's a major advantage. So they are not lost into atmosphere. That means they can, because they are ionic compounds, so they can be recollected and they can be therefore easily recycled. Because they are ionic compounds, they have very high polarizability. They're highly polar, and all kinds of materials can be therefore readily dissolved in this. So very good solvophobic properties. Ability to promote association of reactants in solvent cavity, depending on the ionic liquid. Use of reaction media in biphasic reaction. Yes, we could use this in biphasic reaction also. Wide temperature range. We could do reactions at slightly higher temperature also using ionic liquids. Then task-specific ionic liquids for particular types of action. One could prepare task-specific ionic liquid. For example, I could prepare, or one could prepare acidic ionic liquid, basic ionic liquid, and these could be used as solvent as well as the acid or base could act either as catalyst or as a reagent. Similarly, chiral ionic liquids, we could prepare ionic liquids which are chiral, and therefore in a reaction which is giving rise to chiral products or a basic mixture, a chiral ionic liquid will favor formation of one product, and that's what we had seen, that yes, this will help do away with the process of separation of the enantiomers. Task-specific ionic liquids can also include catalysts. It can are as reagent. So there are a variety of work that has been done on ionic liquids for different applications. As we said earlier, yes, reactions in water. This started with the discovery by Bresco and Greco in early 1980s on the effect of water on rates and selectivities of Gill cell reaction, and these are often recognized as Big Bang in aqueous synthesis. Since then, significant progress has been made in the field of organic synthesis in water. Its advantages include, obviously, this is economically and environmentally attractive. It is inexpensive and abundantly available. It is non-inflammable and non-toxic. It has high heat capacity. It is odorless and colorless. It's a highly polar reaction medium and novel reactivity of therefore organometric complexes, fissile product separation, and catalyst recycling, reduced product contamination, and network of hydrogen bonds which influences the reactivity of different materials. A large number of reactions have been done in water, like chemoselective oxidation of sulfides, enzymatic epoxidation, asymmetric transfer hydration, tin-mediated alylation, and so on. And then we said, why not neat reactions? Reactions under solvent-less condition. Yes, maybe we could all mix all the reactants and then expose to microwave and ultrasound. So we are having no solvent and we are using a technique to make the reaction faster, but solventless. And then there has been recent interest also in multi-component reaction. Reactions which require 3 or 4 steps. Can we all mix them together and heat or expose to microwave ultrasound and achieve the desired product in single step? So these are some of the methodologies which have been applied in recent past to achieve the desired goals. And now we look at some of the applications, the success stories of green chemistry by applying some of these methodologies. Firstly, production of allyl alcohol. See, the traditional route employs reaction of allyl chloride with water, and it generates what is the byproduct? HCl. And we remember from our first lecture that the number one pollutant in the world in terms of release is nothing but HCl. So HCl is a byproduct released in air. How to stop this? This greener route, as shown below, has been proposed, where its reaction is that of propene with acetic acid in presence of oxygen and in presence of catalyst to give allyl acetate, and the water is produced. And this then undergoes hydrolysis by itself to give allyl alcohol and acetic acid, and this allyl acetic acid is then recycled. So what we see in the whole process, the incorporation of a oxygen atom from oxygen. Next, sodium hypochlorite required in large amounts. And we all know the reaction which we have been reading since class 12, reaction of chlorine with NaOH. We know that with production of each mole of NaCl, we are generating 1 mole of NaCl, which is a waste. And I mean, a lot of industries are involved in production of bleach. And the greener approach which has been achieved is to create a concentrated brine solution by dissolving sodium chloride in water and passing electricity through this. The byproduct in this is nothing but hydrogen gas, which is highly inflammable. There's another approach to this, wherein in the brine solution, oxygen is bubbled or added in presence of a catalyst. So 2 NaCl plus O2 gives 2 moles of NaCl without producing any byproduct. In some of these processes, these are patented, and we cannot list the catalysts they're employing. Hydrazine. Hydrazine production, it's again in large quantities, and the process that is employed generally is oxidation of ammonia with sodium hypochlorite. And therefore, people looked at because this itself is a chemical which was producing waste. So people looked at alternative of producing hydrazine, and in the greener process, they use oxidant hydrogen peroxide. And what is the byproduct? Water. So we are using ammonia, hydrogen peroxide, and the byproduct is water. Again, this is a catalytic process. Jones reagent, commonly taught as an oxidizing agent, converting alcohol to a ketone, produces chromium sulfate, and chromium is highly toxic. And therefore, a greener route has come wherein you can oxidize alcohol to ketone, and the byproduct is water with oxygen. And I think this is where the mindset when we teach regular reaction, maybe we should introduce the students that yes, though this is the reaction, but these are the problems, and you should think of, the student should think of new processes, new methods, wherein we can have an alternative and produce a greener reaction. Classical Beer-Villiger reaction, which uses metachloroperbenzoic acid. So it's a stoichiometric reaction. And we produce 1 equivalent of metachlorobenzoic acid. And then came the enzymatic Beer-Villiger oxidation, where they use a biocatalyst, engineered Baker's yeast, and oxygen as a reactant. Because actually this conversion, the incorporation of only oxygen is taking place. So we saw in so many reactions, with sodium hypochlorite or oxidation of propene to allyl alcohol, oxygen, and is cheaply available. Yes, a industrial product. We all know caprolactam, which is the starting material for nylon 6. And the process that we teach is from cyclohexanone to cyclohexanone oxime and then Beckmann rearrangement. And this is starting material. This process, the atom efficiency is only 29%. E factor is very, very high. There is lot of wastage there. And therefore, the industry has come out with a green process. It's called Sumitomo process, green route, where they convert this into oxide using ammonium and hydrogen peroxide in presence of a catalyst. And then again in presence of a catalyst. And this is converted into starting material, that is caprolactam. The atom efficiency increased from 29% to 75%. You can see how much waste has been reduced, and the E factor from 4.5 to almost 0.32. Similarly, another polymer used in nylon 66, adipic acid, is produced from cyclohexanone. Cyclohexanone, we know this, produced from benzene, petrochemicals. This is oxidized to give adipic acid. And since we are using, chemicals, a lot of waste again is generated. And this is expensive. A much cheaper route was therefore identified, wherein adipic acid can be produced from glucose using biotransformations, E. coli, to give muconic acid, which is then reduced to produce adipic acid. So we are using now renewable resource, which is much cheaper and not toxic. Unlike we all know, the starting material benzene, we know it is highly toxic. It's a carcinogen. Production of polycarbonate. Now these are polymers required in large amounts. The kind of plastics that we use, many of the bottles that we use, plastic bottles, are nothing but made up of polycarbonate. The standard process involved the reaction of bisphenol A with the COCl2 and again generating HCl as a byproduct, which is highly toxic. And the greener route therefore employs reaction of bisphenol A with diphenyl carbonate. To make it a little faster, there's a lot of work going on production of polylactic acid from corn. Corn is converted into starch, which is then converted to unrefined glucose, and then by fermentation it's converted to lactic acid, and then a lactide, and then this is converted into polylactic acid. This is a very important polymer, very, very useful polymer. For example, this BASF has developed a composite polyester film called Ecoflex. They are making and marketing fully biodegradable bags, Ecovio, made of this film along with starch and calcium carbonate. The bags completely disintegrate into water and carbon dioxide and biomass in industrial composting system. So you can see this is what we are looking at. Can materials that we are using, can they undergo biodegradation and destroyed automatically? And a lot of work is taking place on polylactic acid for various applications. Production of styrene, again we know polystyrene foam is very useful. Traditional route again required reaction of benzene with ethylene to give this, alternatively from ethyl benzene this, but the greener route avoids benzene and they're using now xylene to produce the byproduct, and more work is underway. Classic route to product brufene, we know, the classic method which was used in an industry involved 7 different steps, and the overall atom efficiency was only 40%. And the waste it was producing in the form of HCl, acetic acid, aluminum waste, HCl, acetic acid, ammonia, and so on. A lot of waste, and atom efficiency was very low. So the industry has modified the process, and this is what is called the hex route. Atom efficiency has gone to 77%, and there's only one waste material, that is acetic acid, being generated. Herbicides have also been produced under green methodology. I'll just be quick. One example of food and drink. We talk of decaf. How decaf is prepared? The coffee beans are often washed free of their unwanted caffeine by soaking them in solvents such as methylene chloride, a suspected carcinogen. But now the process is being modified, and this is being done using carbon dioxide, using supercritical carbon dioxide. So according to European Decaffeinators Association, about 20% of global decaf production now uses supercritical carbon dioxide. The rest is still using methylene chloride. And a lot of other products that we may not be aware how they are prepared use very toxic solvents for their preparation. But now there's a lot of work going on to remove these or to find alternative methodology, and supercritical carbon dioxide is one option. Dry cleaning, which was being done with perchloroethylene, is now being attempted with safer materials like supercritical carbon dioxide. I said in the first lecture, replacing tetramethyl lead, which has now been almost completed. Pharmaceutical industry is working a lot to produce various methodologies. Some of the applications are shown here. Water-based adhesives, even the computer manufacturers are concentrating on removing toxic materials from mundane components. And Apple says that the castings of almost all its products no longer contain brominated flame retardant. Other industries which are working on this, textile industry, paint industry, there are a lot of applications. I have indicated only a few, and therefore we can say that green chemistry is not a solution to all environmental problems, but a fundamental approach to preventing pollution. Thank you. If you have any questions, you can call me at 98106 51142 or write to me at gmkhurana1@yahoo.co.in. Thank you.